Delighted to introduce Delilah. So Delilah received her PhD in physics from Harvard University in 2021 and her Bachelor of Science in Physics and Mathematics from the University of Maryland in College Park in 2015. Before returning to Harvard, she was a postdoctoral fellow of the Princeton Gravity Initiative and the Princeton Future Faculty in the Physical Sciences. Delilah's research focuses on constraining properties of black holes, especially black hole spin, through analytic and semi-analytic methods, which leverage features of black hole space-time geometries and the radiation sourced near black holes. So thank you so much, Delilah. We're delighted to have you here. I'm never going to use that word again. And yeah, the floor is yours.
All right, can you hear me okay? Great.
No, I'm not sure.
About
No, it's just the microphone. I'm not sure. Is it wordable?
is it the light's on?
Okay.
I don't know if it's hearing me.
Can you speak again?
Testing?
Yeah, even that you
Okay.
can hear it.
Yeah,
Okay.
yeah.
Very good.
Touching it, so it's.
Okay. All right. So it's a really it's my pleasure to be here today. Thank you so much for having me. And it's great to follow Riley because he talked a lot about spectroscopy and using it to constrain black hole spin. And today I'm going to talk about, as he mentioned, diving into kind of more theory land, why iron lines, for instance, or any relativistically broadened emission line actually encodes spin and information about the disk which sourced it. So of course, as Riley was mentioning, we're thinking about X-ray reflection, where the corona has shown light onto the disk, and the light is going to re-radiate or reflect the emission as after it's been absorbed and re-emitted. And there are two relativistic effects that mean what would have been a bunch of spikes at the rest frequencies particular to the elements in the disk become blurred. And these relativistic frequency shifting effects are, of course, the motion, the Doppler shift, which can give us both bluer or redder emission from the rest frequency, as well as gravitational redshift, which means we can incur or suffer some extra frequency decreasing to the red. And with these disks, it is the typical assumption, as Riley mentioned, that the inner edge of this disk for reflected emission will be the innermost stable circular orbit. And the innermost stable circular orbit, or ISCO, has its location relative to the black hole horizon being a function of spin itself. As we spin the black hole up faster, the ISCO gets closer and closer to the black hole horizon, meaning it can suffer more redshift for inner parts of the disk. It actually turns out also, if you have favorable viewing inclination, you can also get more blue shifting because the relativistic speeds at which the circular orbiters have to whip around the black hole to maintain fixed radius also increases. And you can actually get the most blue shifting possible as you spin up the disk and view it very close to the plane of the disk. So then, of course, we observe, and we're getting more and more exciting and higher resolution observations as we speak, especially with instruments like PRISM. We can then simulate all the emission, the line, the thermal emission, and whatnot, and try to fit these broadened spectra, which include these broadened lines, to our data to make spin constraints. And of course, as Riley mentioned, we see through this method that a lot of these black holes appear to be rapidly rotating. So for those of you who have studied this subject, I'm sure you're no strangers to staring at a bunch of these line profiles, and these were generated for me courtesy of Laura Redeman. Thank you so much for a project I did when I was in graduate school, where I was thinking about the bluest emission you could get from these lines. But continuing thinking about how these lines encode information about our black hole system, there's all kinds of things you can look at in these lines with respect to their structure, and you notice patterns if you stare at them hard enough. For instance, in this gentle inclination of 30 degrees off the axis about which the black hole spins, you see they all have this common bluest edge. They all have this common bite out of them. They all have these tails as well, and the location of the tail seems to move with spin. For higher inclinations, we see that the the bluer edge seems to move with spin, but not quite monotonically so. And so my desire was to understand what is seeding exactly the structure of these lines physically. And it turns out there's a nice mapping between the behavior of the disk as viewed by you, if you could resolve it on a horizon scale image, and the line profile. So here I have a black hole where I'm viewing it from above, and the bluer side is what's spinning towards me, and I've colored the disk by the redshift factor. That's the ratio of the observed frequency to the emitted rest energy rest frame frequency. And then I've superposed on it these gray lines, which are constant redshift factor, or G. And then beside it, I've drawn the line profile you could draw from it if you just assumed a simple R to the -3 emissivity profile for the disk. And it turns out we can map critical values where the behavior of this line profile changes to the redshift factor constant curves on the image of the disk. In particular, if we look at the bluest and reddest emission that come from the inner edge of the disk, we see that corresponds to, for the red side of the emission from the disk, the reddest emission is my terminal end. And then one of these kinks I have in the center comes from the bluest emission from the inner edge of the disk. If I look at the same for the outer edge of the disk and I trace the levels that correspond to its bluest and reddest emission, I see that gives me the other two kinks where my line profile behavior is changing. And finally, it turns out there's also, as you may have noticed, and now I'm highlighting with this dot, there is a maxima, a local maxima on the disk, which is on neither the inner nor the outer edge, and that corresponds to the terminal blue edge of my line profile. And gives me, so this is kind of a special finite flux point, a single point, which in the limit is giving me finite flux for this nice sharp blue edge. So really what we learn is that the way the redshift of the disk looks painted on the image really is controlling this piecewise description of this function that is the iron line profile, namely the extent, the location of where the behavior changes in a piecewise manner. And it turns out also I can understand which of these edges or kinks corresponds to a local minima or maxima by the relative value. If it's a discontinuity, if it's higher on this side and lower on this side of the discontinuity, this was a local maximum. And then for the ones where it's continuous but a kink, you can look at the relative steepness, which side is steeper approaching from the left or right, and that tells you whether it was a local minima or maxima. And the reason we can understand that this is actually analytically, if I could do an inversion of my formulae, why this would be just a single analytic function that is piecewise, is because you can think about integrating up over the constant redshift factor curves. And what you notice is in each of these regions, A, B, C, and D, the shape of my constant redshift factor curves changes as I jump from one region to the other. And so we made a shorthand for this. So if you look at this region A, all the levels of G are curves that connect the inner edge to itself. In B, we have pairs of curves that connect the inner edge to the outer edge. In C, we have curves that connect the outer edge to itself. And in D, we have closed curves touching neither the inner edge nor the outer edge. And also, because within a specific region A, B, or C, or D, the levels are changing smoothly continuously as you go one to one from other, you can really understand that this is an analytic piecewise function. Even though I can't write it in closed form, if I could invert it, it was really just a nice piecewise function. And then you can give yourself a shorthand using these symbols for what the disk behavior was for those level sets. So learning this, you can say, okay, you gave me one example, but what are all the possible examples? So the terminal ends of the line profile, as well as those kinks, can only occur at the following values. Like I showed you in that example, they can be at the bluest and reddest emission from the inner edge. Those I named G in plus and minus. They can be at the bluest and reddest emission from the outer edge, which I call G out plus or minus, or you can have that terminal point on the disk where you're getting the bluest emission, which I use a G dot for. It turns out if you look at all the possible combinations of spin and inclination and the size that you let the outer edge of your disk be. There are only 10 options for what the configuration of your disk can be. And they have some things in common. The inner edge will always come from the reddest emission from the ISCO, the inner edge of your disk, while the bluest edge of your line profile can be any of these values. So here, if you'll let me abuse my notation of the screen, I have a compactified version of the screen where the outer ring that's dotted is actually infinity. And then you can see the inner edge of the disk, which has the purple line on it. You can see the black hole, and the orange is the outer edge of the disk. And if you were just to look at it from above, each single radius in the disk is one redshift factor. So that's a nice smooth profile. When you tilt your disk slightly, you can get these more exotic examples. Turns out there are 10 of them. And they have different orderings of these different critical values, which order they appear, and some of them can be coincidence with each other in certain configurations, but it turns out there are only 10. To get a sense of why this is, if you think of your disk being infinitely large, when you look at, like I said, when you look at it from above, one radius is one redshift factor, is only one point in your line profile. As soon as you tilt it slightly, the bluest emission is not going to come from your outer edge. It's going to be a competition between getting some of the Doppler motion to give you some blue shifting, and at a gentle inclination, it starts very far from the disk. As you tilt the disk more, it gets driven closer and closer to the disk. Note again that the reddest end of your line is always still coming from the inner edge of your disk. And then if you tilt it even more, that bluest point eventually hits the inner edge of the disk, and you will now lose the region where you have closed curves, and all the curves will end on both, will start and end on the inner edge of the disk. Note that there's these kind of distortions in the shape of the horizon. That would not be on our image in normal scales, just because I've compactified the radius so I can show you a very big screen. And then if you were to think of not going out infinitely large, but plopping down an outer edge, for any of the curves that run into the outer edge, if they were started as circles, they'll now be connecting the outer edge to itself. If they started as connecting the inner edge to itself, they now become a pair of lines connecting the inner and outer edge. If you want more details about that, please feel free to come back to me. But the moral of the story is we can understand that there are only 10 options for what the behavior of these line profiles can be for these sets of kinks that we can get. And because of the things I told you in the first part about relative steepness around these kinks, I can usually see one of these and tell you what order they're in. And because I can tell you what order they're in, I can tell you which ones correspond to the inner edge and which ones correspond to the outer edge. If I know which ones correspond to the inner edge, I can abuse them or leverage them rather to help me think about how I might constrain spin. Okay, so let's take a look at that. So the inner edge of our disk is given to us by the ISCO. So if you look at just for all your sets of spins going from 0 to 1, inclinations going from 0 looking down the spin axis to 90 in the plane of the disk, you can plot out all your redshift factors that you get, as well as you can do the same for the kink corresponding to the bluest part of your ISCO. And so if you could, in principle, view both of these, you could lay them over each other, and you see they give you a map 1-to-1 to spin and inclination. Of course, we can't really observe the red edge because it goes down to 0, there's noise and things like this. But in principle, you could get a bound. Another thing that is useful is in the region where the disk is not too tilted, it's gently tilted enough that you have your bluest edge coming from a point on the disk that is neither at the inner nor outer edge, that finite flux point. You see that that's actually a pretty good constraint of the inclination with which you're viewing. So here, these are the radii that's sourcing that point, that finite flux point on the disk, and this is the associated redshift factor that you get from it. But what's more interesting is if you don't want to have to think about exactly targeting these kinks, or you worry that these kinks are hard to resolve, what you could look at instead of these kinks is just looking at the bluest emission you could have altogether. The bluest emission will always come from, for inclinations under this dotted line, it will always come from that finite flux point. And for this region here, where you don't have a finite flux point, it's always going to be from the inner edge of the disk. And so if you look at these together with the redshift that gives you the red end of your line profile, you also see that you have just from the extent of your disk without having to resolve the sharp kinks in it, but just looking at its extent, taking a ruler across the extent of your iron line, you can make a constraint on spin and inclination. Now, of course, I mentioned that because of these lines have to terminate and you have noise, other lines that are lower in emission as well, you might not be able to all the way resolve them, but if you observe any value of the bluest extent and the reddest extent, you can be sure that your spin and inclination exists in the top right-hand corner of where these lines cut. The true value is somewhere. So it gives you a lower bound on inclination and a lower bound on spin, just by measuring the extent of the line. Here's a kind of a visualization of, now I'm plotting two line profiles for an example, on where they're on a log scale. And now I'm saying, what if I did different cutoffs, which tell me how blue or red I would see it extended to. And for different cutoffs, you can see the true value right here on these dots. And you could be sure that it was here or somewhere in the red. If you could really get all the way down to the actual red value, if you have a different cutoff floors, you push your region out a bit, but your true value is still within that region. Okay, but one thing that is nice to understand now by this mapping and thinking about where the edges and the kinks come from as being sourced by changes in the behavior of the redshift curves on my image of my disk, I can now separate out from the behavior of where the kinks are located, the behavior of the line profile between those kinks and edges. And this is set by the emissivity. So here to give you an example, just using power laws, where I have the power law as r to the minus q. As I change my emissivity, it changes the behavior of my line profile, but what it still exists is where the kinks are located. Now, it can be, in some of these cases, you see the kinks get quite soft, so it might be harder to observe them. But if you were to, instead, because we know that when you calculate the line profiles intensity, there's a factor of g to the minus 3. If you divided this whole thing by g to the minus 3, these lines can stand out a little bit more. These kinks can stand out in the lines a little bit more. But the takeaway is that the geometry of the disk is really setting the location of these kinks. And as long as there's emission supporting them, you'll get a line profile which has sharp kinks in these locations, but the behavior between these kinks is set by the emissivity. And here, for different levels, you can see as I take my two line profiles, as I change, you can look at how the apparent position of the reddest edge and bluest edge change as I move up my the level of my floor, once again, for saying I couldn't observe all the way down to where the line profile drops to 0. In the first case, you only have the reddest edge that you're worried about because you have the case where you have that sharp blue edge since you have that finite flux point. This is the case where you don't have a finite flux point. So this really is not a sharp edge, and so it changes, but it changes much less than the red side as you move up your floor at which you're trying to observe where this kink is located, where this edge is located. Another thing that this now gives us a handle of thinking about trying to study is what happens when we modify our disk motion. So Riley mentioned that one of the things they were thinking about with his student was spin constraints when you have emission from the plunging region. That's the region between the horizon and the ISCO. And so you might ask, how does this change the story here? As Riley showed, you can get bluer emission than you had before from inside the ISCO if you have certain viewing inclinations, and you can always get redder emission no matter what inclination you view at. So if you look at the case of a disk where you're saying, I'm going to let emission go all the way down to the horizon, I'm going to assume the plunging region to have the kind of standard plunging region model where things plunge from the ISCO while maintaining the same conserved quantities, angular momentum, energy as an ISCO orbiter. You can say what happens to what values of my red end, my maximum observable redshift, and my blue end, my maximum observable blue shift are. It turns out for red, of course, if you let the emission go all the way down to the horizon, you're going to be able to get redshift all the way to 0. That's what the horizon is defined as. And in the case of the bluest emission, you see for part of the region where you have that finite flux point on the standard disk, you'll still have the same answer for the bluest region, but if you tilt your disk enough that finite flux point would have hit the ISCO, then when there's stuff inside the ISCO, it can stay a point, but just a point that exists now inside the ISCO for where my bluest emission is coming from. And you see that you systematically bias yourself to have bluer emission available to you, even though you have a lower spin. So if you were to try to make a spin constraint when you don't know how much into the ISCO you're allowing emission, you're going to systematically overestimate your spin. And the amount this is the worst you can do if you let emission go all the way down to the horizon, and the actual amount you'll do bad is determined by when the reflection emission turns off somewhere between the ISCO and the horizon. Another thing you can look at, for instance, is changing the motion of your disk. If you wanted to know how that affects the story, here we've looked at the stable circular orbits on the disk, still terminating at the ISCO, but we speed them up slightly or slow them down slightly. And you see this has an effect where it moves all the kinks left and right. It leaves the shape of the line profile mostly the same, but it waggles the position of these kinks slightly. All right, so that's all I have. So summary, we've now made a mapping for how we can understand what the behavior as far as a piecewise function, noting where the line profile terminates and the relative steepness about these kinks in the piecewise function are. We've now come up with a fully analytic way to decode how we map the disk to the line profile. In the standard model where we just have stable circular orbits, we've described that there are only 10 possibilities. And we've shown that using the extent of the disk or the location of some of these kinks from the inner edge, we're able to constrain the black hole's spin and inclination. These positions are really set by the morphology of the extent of the disk and not by the emissivity. So the emissivity affects the shape a bit, but mostly if we could locate such kinks, we really would be a little bit more robust against worrying too much about the details of emissivity. And we showed that this is all very sensitive on exactly what the model of the disk is doing. If we change the speed of the disk, if we allow plunging region, and we try to make estimates, there are ways in which we could systematically overestimate our spin. And I think this is still, okay, very pie in the sky theoretical. Observationalists might ask, why do we care? But I think this gives us, with this understanding of the morphology of these line profiles, some interesting avenues forward. For instance, we can think about what kind of resolution we need comparing to the kind we're going to get from, say, Prism, and whether we'll be able to observe things like these kinks. And if not these kinks, at least will we be able to observe these sharp blades for the bluer side of these that corresponds to a lot of the inclinations that are available to us for these line profiles when we have that finite flux point giving us the bluest. We can also think, like I said, now that we know that you could pin down the spin and inclination from these kinks themselves, then you could use the shape between the kinks to maybe help you constrain the coronal geometry, which is setting the emissivity. Maybe this is a way to kind of have a bit of a separation in what parts of the line profile you're probing to try to get details about the disk versus things like the emissivity, which would tell us about the corona. And because these models so far that we use for spin and inclination constraints really assume perfectly stable circular orbits. Now that we understand that waggling the motion of the disk moves these kinks a bit, it gives us a way to maybe estimate a little bit of uncertainty from the disk motion slightly. Of course, we expect stable circular orbits to be a really good model, but I don't think it's been asked how good. And then when the stable circular orbits are not a good approximation for what's going on, like in a plunging region, we now have a procedure that we can extend to any kind of disk model you give me. So we can apply it to slim disks, Polish donuts as well, and things like this. Thank you.
Thank you so much, Delilah, for the very interesting talk. Any questions? Or any questions on Zoom? Oh, yeah.
So how free or how general is that model? You've emphasized that the pinpoints don't change. Can you arbitrarily change all the shape in between king points?
I think you could,
And I'm asking because I'm thinking,
yes.
you know, could I fit 6 parameters to a line and get the information out, or do I have to fit 20 or 30 parameters?
That's a really good question. So I think,
I enjoyed your talk.
thank you. That's okay. Very good question. There are a couple of ways you could do it. You could do it completely phenomenologically, where you're going to say, I have an emissivity profile, which I'll break up into chunks of small radii and let them each be a free parameter, and it just kind of tries to do an MCMC to fit the best shape, which is very general. Of course, you could put in a lot of different components to try to fit it. I think it's really not obvious how you should go about backing out the coronal geometry. I think this gives us hints that it could be done, but you do have to pick some kind of basis of functions over which you're going to try to say are a good approximation of the shape, and put some kind of weights on these different components. The number you need, I don't know, but I feel like this is not too dissimilar to the game people are already playing. If you do some kind of geometry of a ring or an extended thing, you then also have to decide how much each position in this extended model is how much that's emitting relative to another radius along this shape anyway. So I think the answer is it's not obvious. You may need a lot of components, I don't know, but if so, it's still a game you need anyway, when you're just prescribing different coronal shapes to then try to model lines with them. So I don't have an obvious answer is the short, but I don't think it's too weird a problem relative to what is already being done as far as how many components you probably need.
Thank you. Any other question? There's one on Zoom, so alrighty. So if you want to unmute yourself and ask.
Yeah, it's me. Great talk, Delilah. I learned a lot from that actually, and some new terms as well. I just wanted to ask then, you mentioned about the potential to look at high resolution actual observable features from these kinks. Is your plan to try to simulate real data with these models and look at which parameters potentially might impact some kind of observable features, and which of your parameters matter? And also, and sorry, it's a little bit of a mean question because it's double layered, but what about the time variability signatures as well? Is there any have you given any thought to that beyond simply the kinks in the spectrum? What these kink regions might do to the predicted time variability signals as well?
Great question, Riley. Okay, so for the first part, is this my plan? I think this would be lovely, but I must admit I'm almost as close to paper and pencil a theorist as one can be, with the help of Python and Mathematica. So if there are people who think this is I'm looking for people who think this is an avenue worth exploring, and I would love to team up with people to try to figure out, when trying to resolve the line profiles with these kinks, kind of at different resolutions, which parameters become most important, which ones become less important. But I don't have a concrete plan to do this at the moment, but if you want to talk more, I'd be happy to. And then to your second question, what was the second question again, Riley?
Time variability.
Time variability. Very good. So, in a sense, at each kind of window of observing, you could play the same game and think of it as each one having its own line profile, where now the inner edge is not necessarily tied to the ISCO. It can be a free parameter. You still have, it turns out I didn't mention it, you still have the same 10 morphologies, as long as the inner edge does not go into the ISCO. If it's anything outside the ISCO but still a stable circular orbit, and you can leave that as a free parameter, and you'll still get kind of similar line profiles. It's just that the inner edge of the line profile itself will not be tied in the exact same way to spin, but with the inner an outer edge using the extent, you can still put a spin constraint. This constraint will get better in the phases where the line profile is coming from the disk when it's really having support extending closer to the ISCO. But you could still use these same insights would apply to every phase in the time sequence. It kind of each is its own line, and then I guess you could also ask questions about stacking them, which I don't know if that's something people already do with data. Try to stack different phases, or if they're always careful to make sure the phases are separated. But in principle, you can apply this insight to each time phase and use the inner edge as a free parameter. You still only have 10 configurations.
Thank you. Any final questions for Delilah? So if not, let's thank Delilah. We'll see you next week. So I think both of you have a busy speaker schedule, so thank you so much.